I don't know if they'll be able to record in very well, but hopefully be able to pull up the PowerPoint decently. So sorry to Kristen and Claire if you can't see this too well. I'll try to focus in a little more. Alright, so to Kristen and Claire, while the others are discussing, a limiting reactant is a chemical that is completely consumed in a chemical reaction. We were discussing this from the Shady Dealings lab. Discussed that in part 1, we had 9 milliliters of calcium nitrate, and that we were adding NaOH, and that NaOH was our limiting reactant. That was all used up, and we would produce more and more solid each time in test tubes 1 through 9. That's how we know NaOH was our limiting reactant. We kept producing more solid. In part 2, 9 milliliters of NaOH was what was added to each test tube. In 1, 2, 3, and 4, we had more solid, while each time we were adding more calcium nitrate. So that was all used up. But in 5 through 9, we ended up with, we weren't producing any more precipitate than the previous one. So NaOH is being all used up. That was our limiting reactant in 5 through 9 of part 2. Our balanced chemical equation is calcium nitrate plus 2 sodium hydroxides yields 1 calcium hydroxide and 2 sodium nitrate. So that's our balanced chemical equation. All right, now for the rest of you, one thing I want to follow through with here before we start on the PowerPoint, I want to focus more specifically on the amount of milliliters that we put into each reaction. Hopefully this will be about right for when the PowerPoint comes up. I may have to adjust. But anyway, in the experiment, if we look at our balanced chemical equation, 2 sodium hydroxides for every 1 calcium nitrate. So this reads 2 things. It reads 2 molecules of sodium hydroxide for every 1 molecule of calcium nitrate. Or it also reads 2 moles of sodium hydroxide for every 1 mole of calcium nitrate. Okay, so these are mole ratios or they're molecule ratios. Makes sense because a mole can equal 6.02 times 10 to the 23rd molecules. So if you have 2 moles to 1 mole, that means you'll have twice as many molecules here as you will there. Moles and molecules are the equivalent of one another. Okay? So we can also use that when comparing volumes. Well, in part 1 here, we had 9 milliliters of calcium nitrate, which means that if we had 9 milliliters of calcium nitrate, what's the most amount of sodium hydroxide that we could have reacted to produce the maximum amount of solid? 18. Very good. So with 9 milliliters, I could have used up to 18 milliliters of sodium hydroxide in order to get the maximum amount of solid produced. So I only here used up half a mil of calcium nitrate, 1 mil, 1.5, 2, 2.5, 3, 3.5, 4, 4.5. So with 9 milliliters sodium hydroxide, with 9 mils of sodium hydroxide, I only used 4.5 of calcium nitrate. But when we got to part 2, now I only had 9 mils of sodium hydroxide. So at 1 mil of calcium nitrate, that means I used 2 mils sodium hydroxide. 2 mils calcium nitrate, 4 sodium hydroxide. 3 calcium nitrate, 6 sodium hydroxide. 4 calcium nitrate, 8 sodium hydroxide. So then once I get to 5, that means that if I want to react 5 mils of calcium nitrate, I'm going to need 10. I only had 9. So the most then I could have reacted, I was easily able to react all 9 of the sodium hydroxide. So in here, that only means 4.5 out of the 5 mils of calcium nitrate reacted. So yes, I did have a little more in 5 than I did in 4, but after 5, everything was the same. Okay? So there's your limiting reactant idea right in play there with our balanced chemical equation. Okay, now to the PowerPoint. So far from that chemical reaction in dealing with the balanced equation, any questions?
No.
Austin?
Yeah.
Yeah. What do you think I'm going to ask you?
Any questions?
No. Doing something?
Oh.
Foot off the table.
Oh.
Thank you. Thank you. Thank you. All right, so let's start with the slideshow here. Away from current slide. So, oops. Bring that up. And there we go.
Beautiful.
We're going to take a look at something called the BCA approach. Let's see how well that turns up there. And not so well. Okay, it's probably about the best I'm going to get it. Unless... Can I borrow your bookcase there?
Go for it.
Thank you. On top of, like that biggest book there that you see, can you grab at the far end of the shelf the biggest book I have there? It's the one on the top shelf. There you go. Perfect. Yep. That one. That works. It's another bio textbook. Sounds like someone needs to get off a chat. Okay. So BCA approach. And I may try to blow this up a little more so it can be seen a little better. That's probably best. So the BCA approach stresses mole relationships based on those coefficients in a chemical reaction. It allows us to set up equilibrium calculations later, and we can show the limiting reactants. Okay? BCA stands for before, change, and after. That's what BCA stands for. Before, change, and after. Okay? So the before, change, after approach. And just so I'm not going too fast, help to keep me in check here. If I am going too fast, let me know. Do I need to stay on the slide, or am I okay to go on to the next? On to the next. Okay. Okay, so just like in last unit, you're going to get a lot more practice with writing chemical equations and then balancing them. So to start with, if you have a chemical reaction that is described there, as you can see, it says, you've got hydrogen sulfide gas, which reacts with oxygen gas. It burns in air. That's what oxygen gas is. You're burning something in air. You get sulfur dioxide and water vapor. The question is, how many moles of oxygen gas will be needed to completely burn 2.4 moles of hydrogen sulfide? Okay, so to start out, you write in hydrogen sulfide, which, by the way, if you get any type of like hydrogen product that you're trying to figure out what it is, you can start with the idea that hydrogen can have a charge of +1, and any other element can be the charge it would be from the other side of the periodic table. any type of acid, hydrogen is always a +1 charge. I know we haven't gone over naming of acids so much. I'll try to do that a little bit more later in this unit. But if you have any questions on what kind of a formula the acid should be, just ask for now. We'll go over acid naming a little more later. Okay, so step 1, balance the equation. 2H2S plus 3O2 yields 2SO2 and 2H2O. That's the chemical reaction, that's how it would balance. So then for the before part, okay, am I good to go on to the next one? Okay. So then in step 2, now you can start filling in everything. 2.4 moles of H2S. That's what you have. So you have 2.4 moles of H2S. That is what the problem is giving you. You have an excess amount of oxygen gas. It didn't specify in the problem how much oxygen gas you have. It just asks you how much hydrogen sulfide do you need to react with oxygen gas. So, and it makes sense, if you're burning something outside, you're burning it in the presence of oxygen. It's what makes a fire go. If the big bad wolf comes up, tries to huff and puff or blow your house down, then he takes a match and lights it, it's going to light on fire because of the oxygen gas that is around it. Only makes sense. How does fire work? It has to breathe like us. Put a fire blanket over it to smother it, to choke it to death. Take away the oxygen source. So, whenever you have a fire, you usually have an excessive amount. The only time you won't have an excessive amount of something is if a problem specifies otherwise for how many reactants that you have. If it tells you how much of one but not the other, you can generally assume excessive. Okay, so, and then in terms of the products, unless they specify the products, how much you have to begin with, you can count on them being 0. Before any reaction, you're generally going to have 0 product. Okay. Am I good to go to the next slide? Okay. Next slide. Step 3. So now what we can do then is we can use these coefficients as ratios to figure out how many moles of oxygen gas we need to react with the hydrogen sulfide, and then how many moles of sulfur dioxide and how many moles of water we should be gaining. Now, for oxygen gas, what I'm going to have to do is take it times the ratio then of 3 to 2. I have 2.4 moles of hydrogen sulfide, so that means I need to take it times a ratio of 3 over 2 to get oxygen gas. In other words, 1.5. So when I take hydrogen sulfide, its ratio of 2.4 times 1.5, I get 3.6. Now with the change with the reactants, when I react to two chemicals in a chemical reaction, I'm going to lose them. So that's what the minus signs are there for. I'm going to lose the amounts of those reactants. So minus 2.4, minus 3.6. In terms of the products, I'm going to gain them, hence the plus 2.4s. And in terms of the ratios, sulfur dioxide, H2S. They're both they're the same ratio, 2 to 2. So if I lose 2.4 of H2S, I gain 2.4 of sulfur dioxide. If I lose 2.4 of hydrogen sulfide, I should also gain 2 moles of water. Reactants consumed minus, products accumulated plus. Making sure I'm ready to go on to the next one. So now, step 4, we can complete the table. So we took care of the before, what was listed. The last slide, we took care of the change, how much we're either going to increase the products by or decrease the reactants, and then we can fill in the after. 2.4 minus 2.4 is 0. Sorry about the slide, it slid everything over. So this should be 0. Excess minus 3.6 is still excess. You have no idea how much oxygen gas there is in the world, so it should usually be in excess. Sulfur dioxide, we had 0 to start with, we should have 2.4 to end it with. And then the same thing for water vapor. 0 to start with, 2.4 to end with. Okay? Now, that works great if the question is asking for moles. But what happens if we're trying to figure out grams of, say if we want to find out grams of water that we'd form. I've got moles of water. How do I turn that into grams of water? See what you remember from previous. If I have moles of water, how do I turn that into grams? What do I got to do with this here?
Atomic mass.
Atomic mass. Yep. Also known as molar mass. So I got to find the molar mass of water. Well, water is 2 hydrogens, 1 oxygen. 1 oxygen is 16, 2 hydrogens are 2, 16 plus 2 is 18. So 1 mole of water has 18 grams in terms of a mass. So 1 mole of water equals 18 grams. So if I've got 2.4 moles of water, that means I've got to multiply 2.4 moles times 18 grams to get how many grams of water I've got. Or like they did with oxygen gas here, if I've got 3.6 moles of oxygen gas, I got to go to my periodic table, find out the molar mass of a single oxygen atom. The formula of it is 2 oxygen atoms make a molecule, so 16 plus 16 is 32. 3.6 moles times 32 grams per mole gives us 115 grams. So we're converting moles to grams. Okay. So if I have moles, I got to convert it back to grams and multiply by grams to get back to grams of my substance. And as stated before, only moles go in your BCA table, as moles are the thing that we can compare everything with. Our coefficients in our chemical reaction, in order to balance the equation, those are molar ratios. So the balanced equation deals with how many moles, not how much in terms of grams. So if you are given the mass of a reactant or a product in grams, you're going to have to turn that into moles first before you can use the table to convert things. So if you have grams, you're going to have to convert to moles first. Then once you figure out moles, you should be good to convert the moles of what you're looking for back into grams. Okay, so I'll give you a couple, actually I think I've got one more limiting reactant problem from here. And then if there's enough time, I'll get started into some an example one. And what we'll end up then doing tomorrow is we'll finish up with 2 more examples, and then I'll set you loose on homework the rest of the hour. So tomorrow will basically be time spent working on worksheet 1. Worksheet 1 was shared with you already. You don't have to do it now, obviously, but if you wanted to, you could. That'll end up being tomorrow night's homework assignment. All right, so the question that we are given here, when half of a mole of aluminum reacts with 0.72 moles of iodine to form aluminum iodide, how many moles of the excess reactant will remain? How many moles of aluminum iodine will be formed? So we have to start with writing out the chemical reaction. Aluminum plus iodide yields aluminum iodide. Iodine is a diatomic molecule, just like bromine and chlorine and fluorine and oxygen and sulfur and nitrogen. They're all diatomic. Those are the ones that are commonly diatomic. So the ones that are in column number 7, and then along with oxygen gas, sulfur gas, nitrogen gas, those are all 2-atom molecules. So aluminum plus iodide yields aluminum iodide. So then balance it, 2, 3, 2. For the before, we can put in 0.50 moles of aluminum, 0.72 moles of iodine. And of course 0 for the aluminum iodide because we don't know how much we're going to, it doesn't tell us how much we have yet. So that's the before. So now the next step, what we have to do then is figure out which one is the limiting reactant based on our how much we would need of one versus the other. So what they did in the next slide here is they decided to say, okay, what if aluminum is the limiting reactant? They're using a guess and check method. So if aluminum was the limiting reactant, then they took 0.5 moles of aluminum times 3 over 2, because that's the amount of iodine used for every aluminum. 3 iodines for every 2 aluminums. So they took 0.5 times 1.5, and they got 0.75. Well, as you can see, we've got more. We've got more here than what we can react, and we can't have such a thing as a negative amount of a reactant. So that means iodine must be the limiting reactant, because there's not enough iodine here. We cannot use 0.75 when we only have 0.72. So now what we have to do then is take the 0.72 iodine times 2 aluminums for every 3 iodines. In other words, take 2.72 times 2/3. So 0.72 times 2/3 gives you 0.48. So we're going to use all 0.72 moles of iodine. We'll end up using 0.48 moles of aluminum. And we will end up gaining then 0.48 moles of aluminum iodide. As you can see, the ratio of aluminum to aluminum iodide is the same, 2 to 2. Lose 0.48, gain 0.48. So we end up with, after 0.02 moles of aluminum, all the iodine is reacted, and we end up gaining 0.48 moles of aluminum iodide. That's really all I got, other than next slide just has a couple of comments. Otherwise, for where we're at right now, tomorrow we'll go over some examples, questions so far over the how to do any of the converting. You're going to be using a lot of proportions, just as giving you a heads up. You're going to be having to do a lot of proportional thinking, a lot of using converting, fractions, etc. Okay, we'll stop right there. and we'll pick it up tomorrow with examples.
Bye, have a great time.